Hey guys, Professor Doney back. Right now we're going to be talking about work and energy, the concepts of work and of energy. We do that, besides it being in the book, because energy is conserved and they are scalars. Energy is a scalar. Conserved means we don't lose it so we can keep track of it, and scalar means we don't have to deal with the vector stuff. Alright? Now, energy is the ability to do work. What is work? Work is when work is done when I have a force that acts through a displacement, basically moves an object, right? Acts over a distance. Now, if that object happens to have a force acting at an angle, like in this situation, then I have to make sure that force is parallel. I always want it in the same line or lining up with parallel-wise distance. Okay? Now, it could be against, like friction, but we want to make sure it's lined up with a parallel. Alright, so let's just do a quick example here. Apologize for my handwriting. Let's make that 100 at 30 degrees, and that's going to sit on the table here. The mass is going to be our 10 kilogram box as always, and let's use a coefficient of, I don't know, 0.4. Okay, first thing we should always do when we see the angle is break that up. And we're going to break that up as we make our free body diagram. This is all stuff we should already know. It has mg, there's f of n because of the table. I break that up in the horizontal, will be 100 cosine and 100 sine up. That makes 50 up. And since we are given friction, we're going to say that friction is going to oppose it and try to hold it back this way. Okay. So that's from the 100 cosine 30. This is from the 100 sine 30, which is going to make the box appear a little bit lighter. So let's look in the y direction first. Sum the forces. Hello. Sum the forces in the y direction. Set it equal to 0 because we're assuming it doesn't move. We're going to have a 50 up plus an f of n up minus an mg equals 0. Tells us that f of n equals mg minus 50 if mass is 10. Times gravity 9.8, that comes out to be, what's that, 48 newtons. Okay, that's friction. Our normal force, sorry. Once we have the normal force, we can go back in and say, alright, let's find out how much friction we have then in the x direction. Comes from the FUN equation, 0.4 times 48. And I'm going to try to do that in my head. There's going to be a 2 there, a 3 is 16, 19.2 newtons. Somebody can check and let me know that's wrong. But alright, that tells us how much friction is acting back. So this is going to be 19.2 the other way. So now we look horizontally, we can see it is going to move that way, but it is going to oppose friction. But let's find out how much work is done by this force. So the work done by the 86 is the force, which is 86, times displacement. Let's make it 10 meters. We're going to move this object 10 meters. Didn't add that in there. We drag it 10 meters, slide it 10 meters. It tells us we do 86.0 newton meters of work, which is 860 joules. And my handwriting is getting bad. I apologize. Now the work done by the friction, just so we can compare here, since friction is a negative because it opposes motion, is going to be a minus 19.2 times the 10 meters we drug it. That's minus 192 joules. The minus sign tells us that work or energy was taken out of this system. Lost by a system usually takes it out as rubbing and turns it into heat and it's wasted. The 860 is the work that we put into moving the box. Okay? So just a different way of looking at how to get work and energy. A couple other things we can do with this, but that's sort of the basics. So hope that helped you out, and you understand the positive negative idea of it, and we'll see you next video.